This is Jack Jackson again with another in our series of lectures. This one is on a continuous distribution. The easiest one we can think of is called a uniform distribution. We're going to look at uniform distributions in this video. And in the process, we hope to get a good idea from this simplest example of how we can compute probabilities from the graphs of CDF or PDF. We can look at what the formula of a CDF and a PDF tell us, and so forth. And so we'll be able to see some of the general ideas about continuous distributions, and also look at this particular example as a class of examples. So a uniform distribution, pretty simple. The PDF graph is just a horizontal line segment of uniform height on some interval, say from A to B, and it's 0 everywhere else. So if you look, here we have this particular one is the graph of uniform 3, 7. What that means is the A is 3 and the B is 7. So between 3 and 7 on the x-axis here, here's 3 at the left and 7 on the right. Between there we have a bar, or just a horizontal line segment graph going straight across. And everywhere else it's 0. So we have down here. So really we can pretty much ignore the stuff outside of this and really only concern ourselves with what happens between this 3 and 7. Really within this little rectangle here is everything that's really of interest to us. Anything outside of that, just 0 probability. So here's a question for you. What is the height of that line segment? Let's go ahead and figure that out. Press pause now. Well, let's come back and take a look at this. We're trying to figure out what the height is going to be. Now we know that this goes from 3 to 7. We should be able to figure out the height. Notice this one I didn't give you the y-axis, but we can figure it out anyway. The thing to remember is that probabilities are areas. Okay? And so if we look at the total area, it's the area between the graph, the red graph, the graph of the PDF, and then the x-axis, which actually is the same as the graph over here to the left of A, the left of 3, and to the right of B, which is to the right of 7. But in between, we have areas we can actually get. And if we look at the whole area, the area of that gray rectangle, well, what is the whole probability of anything happening? Well, it's got to be 1. So we know from any continuous distribution that the areas between the graph of the PDF and the x-axis are probabilities. If we put all the area between the graph of the PDF and the x-axis, we get a total area of 1. So we're just saying that the area of that rectangle is 1. Well, can you now figure out what the height is? If you don't have it already, press pause now and figure it out. Okay, well, we know the area is 1. We can figure out, well, what's the area of a rectangle? We know how to do that. It's just length times width, or base times height. So the base here along the x-axis is just, well, it's going from 3 to 7. So what is that? That's 7 minus 3. That's just a length of 4. And so then what's the height? Well, the base, or the width of the base, or width there, is 7 minus 3 is 4. And the area is 1, but the area is also that base of 4 times the height. So the height of that rectangle must be 1 over whatever that base was, or 1 over the width. And the width was 4. So we get the height must be 1 over 4. Can we come up with a general formula for a uniform distribution that goes from A to B? Go ahead and figure out what that would be in general. Press pause now. Okay, well, we're back. All we have to do to figure this out is just where the 7 is, we replace it by B, and where the 3 is, replace it by A. And so we know that the PDF of x, P of x, or PDF of x, is 1 over B minus A. Because what is that B minus A? That's the width of that bottom of that rectangle, or the base of that rectangle. And then the height of that rectangle is the y value of the PDF, and that's going to be 1 over the base, because when you multiply them together, you got to get 1. Of course, that base has length B minus A, and so the probability density function, PDF of x, is 1 over B minus A. And that applies between A and B, inclusive. But if it's anywhere else, it has a value of 0. So write down the formula and graph for a uniform 411. Go ahead and figure this out now. Press pause. Okay, well, we're back. From 4 to 11 is a length of 7. That's 11 minus 4 equals 7. So the height of the PDF, the height of our graph on the part where it's not 0 is 1/7. And so the P of x, or PDF of x, equals 1/7 for x is going between 4 and 11. And it's 0 otherwise. So you can see that shaded in red there. And of course the y scale is not, should be added onto that. Should be, see the y-axis, which I didn't graph here, but the y-axis is going to show us going up to 1/7 for the height. So for this distribution, see if you could go ahead and compute and illustrate the following probabilities. First, what's the probability that x is less than 7? What's the probability that x is greater than 5? And then what's the probability that x is between 6 and 9? You should be able to illustrate these as areas on the graph of the PDF, and then you can also compute them, compute numbers for them, compute probabilities. Please do this. Press pause now. Okay, let's check your work here and see if you were able to do this. Well, what we're really doing when we're finding probabilities when we have a continuous CDF is we're computing areas. And in this case, this is why I started with this one, we're just finding areas of rectangles. That's pretty easy to do. We've been doing that since we were in elementary school. So we're just finding areas. And so when we're saying what's the probability that x is less than 7, well, first of all, notice that there is no area or no probability to add up for anything between, well, anything less than whatever a is. In this case, that's 4. Anything less than 4, there is no area. So there's nothing way over here to the left that's going to work to give us any area. But when we start at 4 and go to 7, that does produce some area. That's a rectangle there from 4 to 7, and so that has a width or a base of 7 minus 4, and then we go, of course we know the height now is uniform, and we already figured out that that would be 1/7 if it's uniform from 4 to 11. From 4 all the way to 11 is a length of 7, and so that means the height of the big rectangle going all the way from 4 to 7 and up, so the top of that rectangle would be the entire red bar that's elevated there, has to have a height of 1/7. So, well, work that out, you get 3/7. Similarly, we want to find the probability that x is greater than 5. Notice that there is no nothing bigger than whatever b is, in this case 11. So there's nothing bigger than 11. So when I say the probability of x is greater than 5, in this case, that's really just the probability that x is between 5 and 11. And of course that gives us that shaded rectangle there that you see in the middle. And of course that's 11 minus 5 is 6 for the base, and then the height is 1/7. Multiply those together, you get 6/7. If we want to go between 6 and 9, then that's 9 minus 6 is a base of 3 and a height of 1/7, so that's a total of 3/7 for that area. So the areas here are the probabilities. So the area less than 7, the probability of x is less than 7 is this area really from just 4 to 7, which is a rectangular shape, easy to find the probability. The probability that x is greater than 5, really 5 to infinity, but we really don't have anything from 11 to infinity, so it's just 5 to 11. And that probability gives us an area, or that area is a probability, and we compute it to be 6/7. And similarly from 6 to 9, we find the area to be 3/7. So if we summarize what we just figured out and sort of generalize it to arbitrary letters, we know the probability density function, PDF of x, or I'm just going to use P of x, little p of x for the PDF. It is 1 over b minus a for x's between a and b inclusive, and it's 0 otherwise. The graph looks like a horizontal red bar going from minus infinity up to a, and then also one from b going to infinity, and those are both on the x-axis at 0. But in between is the interesting part. From A to B, we have a bar of height 1 over B minus A, and it's just a horizontal bar, horizontal line segment. We do the probability that C is less than or equal to X is less than or equal to D is the same as the probability of C is less than X, which is less than D. Now remember, in the continuous cases, the probability that X actually equals C or X equals D, those probabilities are actually 0. There is no area over a single point. A single point has no width, so even though we have a height, there is no width, and so there is no area. So whether or not you include the endpoints is really totally irrelevant in a continuous case. It makes a big difference in a discrete case, but it does not make a difference in the continuous case. So whether we say probability of C is less than or equal to X, which is less than or equal to D, or just the probability of C is less than X, less than D, we're still finding the area of this same rectangle. And its base will be D minus C, and its height will be 1 over B minus A, so we get D minus C over B minus A. And this will work for any C's and D's. Well, we got to get these in the order, so we want A, then C, then D, then B for this to work. So A is less than or equal to C, which is less than or equal to D, which is less than or equal to B. Again, the biggest point that's very important is areas under the CDF are probabilities. And in this case, areas are pretty easy to compute because they're just rectangles. Alright, let's do a real-world example now. A bus company claims that its buses never leave a stop before the scheduled time, but are sometimes late. They also claim that in the afternoon, the amount that they leave the bus stop late, is uniformly distributed, and the buses are never more than 10 minutes late. If we assume their claims are true, see if you can find out these things here. So we want to obtain a formula and graph of the PDF for X, which is the number of minutes the bus is late. What's the probability the bus leaves within 3 minutes of the scheduled time? And what is the probability the bus will be more than 6 minutes late? So see if you can do those 3 tasks for this particular scenario. Go ahead and do that now. Press pause. Well, you've been looking at this bus problem, and so notice that they say it is a uniform distribution, and we know that they're never early, or they never leave early anyway. They'll just wait at the stop till their scheduled time to leave if they get there early. And so that means the probability that it's less than 0 is 0. So your A is 0. And they're never more than 10 minutes late, so the probability that's bigger than 10 is 0. So the only thing that's going to happen there is it's going to have some values besides 0 or between 0 and 10. So that's your A and your B. A is 0, B is 10. And so this is uniform from 0 to 10. So if we graph it, here's what we get. We get a bar, a horizontal graph from 0 to 10. It's on the x-axis otherwise. And of course the height will be 1 over the base for that bar, or the how far it is. So in other words, 1 over B minus A. 10 minus 0 is 10. So that's 1/10, or 0.1, which is the probability there of, was a probability density function, PDF. So what's the probability that the bus leaves within 3 minutes? Well, within 3 minutes means anywhere from 3 minutes early to 3 minutes late. So that's the probability that -3 is less than X, which is less than 3. But we already said that there is no way that they're ever going to leave early. That probability is 0. So that translates down to really just the probability that 0 is less than X, which is less than 3. In other words, it's between right on time at 0 or 3 minutes late, which is 3, and it's sometime within that. Can't be less. Can't be negative in this case, just because they promised us that it never leaves early. And assuming they're correct, that probability is 0. And so we're finding the probability that X is between 0 and 3. So we're looking at the area of that shaded rectangle, which has a base 3 minus 0, or 3, and a height of 1/10. So that's 3/10, or 0.3, or 30%. What's the probability that the bus will be more than 6 minutes late? Well, that's the probability that X is greater than 6. Well, again, there's a bunch of 0 probability stuff out there. If it's bigger than 10, there's a 0 probability of that happening, assuming their claim is correct, that they never have a bus late. And so the probability that x is greater than 6 is just the probability that x is between 6 and 10. And that has a rectangle there that you see at the bottom, and that rectangle's area is the probability that we're looking for. Its width or base is 10 minus 6, which is 4, and its height, once again, is 1/10. So we have 4/10, which is reduced fraction form is 2/5, decimals 0.4, and percentage is 40%. Alright, let's do another exercise here. Let's let x be a uniform 5/10. Hopefully by now we know what that notation means. And I've got a bunch of probabilities that we want to get, and we're going to organize them ultimately here in a table, a CDF table. Now remember, the CDF is the probability that x is less than or equal to the x value. So what we're looking at, all these are probabilities that x is less than or equal to a number, or remember, since it's continuous, we can say probability that x is less than or equal to 4, or probability that x is less than 4, same thing. So these are CDF values. So let's figure these out. Probability that x is less than 4, x is less than 4.5, and so forth. I've got this in a nice table so that the numbers on the right there start at 4 and go up by 0.5 each time. Go ahead and figure out what all these are for a uniform 5/10. Press pause now. Well, that may have taken a few minutes to figure that out, draw a graph, and compute some areas of a bunch of rectangles. But after a while, I think you probably notice some patterns here as well. Okay, so we're looking at this graph here. From 5 to 10, it is the bar is up there with height of 10 minus 5 is 5, so that's actually the width, and the height was always the reciprocal of that. So the height is the reciprocal of the width. And so this is 1/5 or 0.2. And so notice any of these that are less than 5 or 5 itself, they'll have a probability of 0. So the probability that x is less than 4, 0. Probability that x is less than 4.5, 0. Probability that x is less than 5, 0. But now when you get to 5.5, now we've got an area between between 5 and 5.5, we have a rectangle that has some area that goes up, and we can figure its width is 0.5, its height is 0.2, that's 0.1 when we multiply them. Similarly, we go out to x less than 6. What we're really doing is between 5 and 6. So between 5 and 6 is a width of 1, and again the height, if we're in that middle part, it's always 0.2. And so 1 times 0.2 is 0.2. And similarly, we can go through here and figure out every one of these. So if you would, try to get an idea of figuring these out. And we're just adding more and more area accumulating. Notice that by the time we get to 10, we have a width of 5 and a height of 1/5. We have a total area of 1, just what we expect. And anything past that, we've already accumulated all the area, and so it's not adding any more, so all those probabilities are also 1. Go ahead and take a minute to really make sure you got all these numbers right and that you understand them before we move on. Press pause now. Well, now that we're back, let's see if we can put these things actually in a table. And this will be a table for the CDF function. If you haven't done that already, press pause again and do that now. Well, here it is. We have x's and then the CDF function of x, which starts at 0 and ends at 1. CDFs always start at 0 and end at 1, and then they go up in the middle somewhere. Now what I'd like you to do is get out a piece of graph paper and make carefully mark out from 4 to 11.5 or 4 to 12. Actually write out mark this out carefully on the graph, and then make sure your heights are marked out carefully. And we're going to go up from, say, 0 to 1 on the height, and you want to have enough grid lines there that you can work this out carefully. And plot dots for all these, and then eventually connect your dots. And this should be the graph of the CDF. Go ahead and do that now, and we'll check it against what I've got in a minute. Go ahead and do that now. Press pause. Okay, well, we're back. What you should have gotten is something like this. Every time we're over here to the left, we're at 0 to the left of A. And once you get to A, which in this case is 5, it's still 0. When you're at B, it's 1, and it's 1 from there on. So we know we've got a horizontal line array here at 0 up to A. From negative infinity to A will be at 0. And we know from B on, which is 10, from 10 on it will be at 1. And it turns out the dots that you came up with should have all been in a straight line. And so in fact, what you really get is a straight line piece connecting these up. So notice in general, how does the PDF and the CDF compare? So notice I have a particular spot located here. Right at the moment, I'm at 9 for K. Okay? And so the probability that X is less than K, X is less than 9, is the area of this shaded yellow rectangle. But that's also the height of the curve of the CDF curve. So Y values on the CDF are actually probabilities. Y values on the PDF are not probabilities. Areas under the PDF are probabilities. So the yellow area is a probability. That's how you see it on the CDF curve. But on the PDF curve, the PDF curve is the red one. The probability density curve, the PDF, the area there under it, the yellow rectangle, is the probability. But the height of the purple curve, which is the CDF curve, that Y value of that point is also the same as that yellow area, and that's the probability. So once again, on the CDF, that's the purple one, cumulative density function, the output of it, the Y values, are actually probabilities, the probability that X is less than or equal to that point. Y values on the PDF are not probabilities, rather the areas under the PDF are probabilities. So can we come up with the CDF formula? We had a PDF formula, wasn't too hard to come up with. Well, what do we know? We know it goes through this point. Well, we know it's 0 over here, 1 up here, and it's linear in between. Can you come up with any part of this? Well, the easy part, it's the CDF of X equals 0 if X is less than A, and CDF of X equals 1 if X is greater than B. But what about in between A and B? Well, it's linear. You guys know a lot about linear functions from your junior high and high school courses and college algebra courses, places like that. Somewhere along the line, I know you've studied about linear functions. So what do we know? We know it goes through the point A0 and B1. Can you use that to figure out a formula? Go ahead and do that now. Press pause. Well, one way that we might remember is that anything that is a line in general that goes through an x-intercept of A, 0, and it has slope m, we'll have the formula y equals m times parentheses x minus a. That's kind of like that's a slope x-intercept form of a line, or a slope root form. It's also basically the point slope formula, where we have a particular point that's on the x-axis. So remember so we know that that the a is the x-axis where it crosses, so it's x minus a. The question then is, we just got to figure out the slope. Well, the height of this is 1. Okay, so the delta y is 1 as we go from this point A, 0 to B, 1. We're increasing the y's by 1, so delta y is 1. And delta x, it's just going to be from A to B, which is B minus A. So delta y over delta x is 1 over B minus A, and that's your slope. So your formula is 1 over B minus A times x minus A. or just x minus a over b minus a. So there's your formula for the CDF. It's x minus a over b minus a. Between a and b, it's 0 if x is less than a and 1 if x is greater than b. Of course, if x equals b, it's 1 also, and if x equals 0, x equals a, it's also 0. And so you can see that. So there's the graph and the formula in general for a CDF. So let's go back and review. For a uniform PDF, the formula is P of x equals 1 over b minus a from x going from a to b and 0 otherwise. And so the graph looks like this. You've got horizontal bar pieces, 3 different ones. 2 of them are on the x-axis at 0. Those are rays going from minus infinity to a and from b to infinity. And the y value is 0 for those. And then you have a horizontal bar, a horizontal line segment going from x is a to x equals b. And then the y's are all the same. They're 1 over b minus a. So that bar has length 1 over b minus a. Well, has length has b minus a, and height 1 over b minus a. And if you're finding the probability that x is between c and d, and this is incorrect here. This should say a is less than or equal to c is less than or equal to d, which is less than or equal to b. So I'll fix that on the slide. And so this is a, then this is b here, and then in between we got c and d. So as long as you got them in order, they should be in the order a, c, d, b. So if you're in that order, then you're finding an area of a rectangle here, and your rectangle goes from c to d, so it's d minus c for the numerator, and the numerator is for the numerator, and the denominator is b minus a because your height is 1 over b minus a. Here again is a comparison of the uniform graph of the CDF in red. No, CDF is the purple one. PDF is the red one. So the red one is the PDF, probability density function, that's on the top. And then the CDF, cumulative density function, is in purple. So in general, CDFs are going to start at 0 on the left and end at 1 on the right, and somehow they're connected and go up, increasing. They always increase. They might level out for a while, but they never go back down. They always accumulate probability as they go left to right. So the CDF is always an increasing function. And you can see the formulas. Now, once again, how does this compare? How do the PDF and CDF connect to each other? Well, we can see here that once again, that if we want to find a probability, we need to find it as an area under the PDF, that's the red curve, or it's a y value on the CDF, that's the purple one. So I've picked a particular k value here, and from this particular k value, we have the we can go up to the point on the CDF, the purple curve, and go across and find its y value or the y coordinate at that point, and that's going to be the probability. And that turns out to be exactly the same. The probability what? The probability that x is less than or equal to this k, or the probability that x is less than that k. The equal to is 0. Doesn't matter on that part. So the probability that x is less than k, or the probability that x is less than or equal to k, is the y value on the purple curve, on the CDF curve. On the PDF curve, what we do is we go up, we make an area of that rectangle, and that area is the probability. So the yellow area of that rectangle is the same as the y value or output value or height, second coordinate, of that particular point on the CDF. Now we have some parameters here. I think it's not too hard to see that the mean and the median are both the same here. Remember, the median is the point where half the area is below it. Well, I think you can see that half the area is going to happen exactly halfway between A and B. And of course, to find a number halfway between two others, we're just finding their mean, or their average, in other words. So we just do A plus B divided by 2. Now that's also the mean because that's the balance point. I think it's pretty easy to see that if we shaded in all of our area with that total rectangle of area 1, that the balance point in the middle would be exactly halfway between A and B. So the mean and the median are the same. It's a little harder to figure out the formula for the variance, and I'm not going to go over how this was derived, but I will just give it to you here for reference. It turns out to be b minus a squared over 12. And again, that takes a little bit to explain why that works, so I'm not going to bother with it right now, but just it's there for reference if you ever need it. And of course then the standard deviation then would just be, well, take the square root of that, it would be b minus a over the square root of 12. And this one's not too hard to see. The skewness is actually 0. In other words, that means it's completely symmetric about the mean. And I think you can see that from the picture that it's going to be symmetric about the mean. Next, I want to show you some things here real quickly in this Geometry Sketchpad sketch so you can see some of this a little bit dynamically. So, I'm going to show you the PDF graph here. And so there's the graph of the PDF, and it goes from A to B. And I can go up here in this particular example and type in numbers that I want for A and B. So right now A is 5 and B is 10, but I can change it. Let's say, suppose I go from 2 to 10. Notice that's going to make it wider, but it also makes it shorter there because the total area has to be 1 there. So we can change that, and this is dynamically works out. So I can actually click on this and hit plus and see it increase a little bit at a time, or minus. And it's a little bit harder to see this, but I think you may notice that as I'm hitting minus point on B, B is coming in to the left, which is making that rectangle that's actually going to have some area under it smaller in width, but larger in height. So let's just go from 2 to 5, for example. And so that rectangle has area 1. Now, if we want to find some probabilities, what we're doing is we're finding these areas. Okay? And this one is set up, let's see which points. It looks like the points at the top are the ones you can slide. So I can slide points left and right here, and we can see from this information right here that these are the points, well, at the bottom we see points E and F, and points E and F we can slide and see what they are. This tells us what those points are, but it also tells us that probability, which is just the area of that rectangle. Also, how tall is the rectangle? Well, if we go all the way out, remember that area is 1. Okay? And so, how wide is it? Well, it's going to be B minus A. In this case, that's 5 minus 3. And if you notice right here, that's already computed for us, which is 3. It just does that subtraction for us. And then if we do the reciprocal of that, that's going to be the height, because we need to multiply these two numbers, which are the lengths here, the width here, and the height here. If we multiply those, we get the area of that rectangle, but we know that rectangle has to have area 1. So this one's also set up where we can go in and compute some areas. So, for example, what if I want to find, if I give this numbers that are outside of my rectangle, it doesn't really work right. Okay, so you have to, well, let's see here. So if I go from, say, 3 to, actually it looks like the top is working right, 3 to 8, it's going to knock that 8 down to 5 because there's nothing between 5 and 8. So we're going from 5, really from 3 to 5. But let's go ahead and make this something smaller. Let's say 4.5. Okay, so we're going for from 3 to 4.5, and that tells us that 4.5 minus 3 is 1.5, so that 1.5 is the width of this bottom of this thing, and the height is always 1 over b minus a. Okay, 1/3 in this case, and so we get that area is 0.5. So that's half of the area. There's a probability is 1/2 that will get some x value between 3 and 5. So if the x's are uniformly distributed from 2 to 5, and I pick one at random, the probability that it will be something chosen that is between 3 and 4.5 is 50%. If we, let's see, so the formula in general is here. That shows up there. PDF of x is 1 over b minus a for x's between a and b and 0 otherwise. The CDF graph is going to come in at 0 here. It's going to have to end at 1. And in between, it's a straight line. So if this one's a horizontal line, this one has to be a straight line, but not horizontal. So y values, it always goes from 0 to 1. X values, it always goes from a to b. So remember that what we want to do is take this and figure out areas. So notice as I'm over here to the left of this, the probability is 0. But as I get to A, the probability is still 0 at A. But if I go a little bit to the right, notice what's happening. I'm finding the area of this rectangle, and that's the probability, but that's also the y value on this curve, on the purple curve. So that's the rectangle, which is a rectangle underneath the red PDF curve. Okay, so it's an area under the PDF curve, but it's also a y value on the CDF curve. So this is in general for continuous distributions. This happens. Now this one's pretty easy, so that these always turn out to be rectangles, pretty easy to compute. And we see that as we move from the left, this starts at 0, and that area is accumulating more and more area, so the height on the CDF is going up and up, until finally we get to this point here at B, and we're already at 1 for the height. And anything beyond that, as we go to the right, turns out to have just a height of 1. So hopefully you get to see the connection here dynamically between the area and the height. And of course then the CDF formula turns out to be this. CDF of some k value is k minus a over b minus a for k is between a and b, and if k is less than a, it's 0, and if it's bigger than b, it's 1. So that's uniform distributions, and hopefully along the way we were able to figure out a little bit about what it means to be not only a uniform distribution, but just in general what it means to talk about the PDF and the CDF of a continuous distribution.